I would like to remind you the idea of Adler-Kostenheim scheme applied to the full symmetric Toda system. And there were some questions about the action of the Lie group, Lie algebras. So I will start with some reminder of this concept. So finish. G acts on a set. If there's a map, nice to meet you. There's a map from G to the group out of X. It's a group of automorphisms of the set X. So it's a group, and we ask that this is a homomorphism of groups. So of G1, G2 applied to some element X in X. It should be tau G1 applied tau G2 applied to X. See? Definition rho from G to end of V. There V is a vector space. Is a linear representation of G if it's a homomorphism of if rho is a homomorphism of groups G to invertible linear automorphisms inside all linear maps from V2. We discussed examples. Example. Let G be the group S3, the symmetric group. When we can realize this symmetric group as linear operators, the most simple way is to map it S3 to GL3. Rho of sigma applied to the vector I is E sigma I. So it means that in our three-dimensional space, rho of sigma 1, 2 is a matrix okay. Example 1, example 2, let group be So it's some trivial example, but for example, let group be SL2. So the fundamental representation of this group is given by its inclusion matrices 2 by 2 over R. But it is also a linear representation of the group SL2. Okay. So what is the what is meant as an action of the Lie algebra? Let us say firstly about a linear, about the linear representation. Rho from the Lie algebra to and V is a linear representation of G on V if rho is a homomorphism of Lie algebras. So this linear space, the space of linear maps on the space V is obviously an associative algebra, but is also a Lie algebra with operation commutator. Is it clear? What do you think? We can always consider some commutator. So if A and B are elements of A and V, just linear operation. So we can consider the multiplication as linear maps, as linear operators. But we can also consider the commutator, and it gives us a Lie algebra structure on the same linear space. So we say that there is some linear representation if so if each element of the Lie algebra acts in some way on this linear space by some linear operator, but moreover if we consider commutators, so what rho of x and y applied to vector v. So you see x and y are elements of the Lie algebra G. We can consider the commutator inside the Lie algebra and then apply our map. So we obtain some linear operator on the space V. We can apply it to this vector V, and it should be the same as the commutator of two linear operators. So here it's the commutator of linear operators as elements of this space of linear operators, and we have to apply it to V, or if you like, rho of x applied to rho of y applied to V minus of y applied rho of x applied to V. So this is the commutator of linear operator on the space V. Remark. There is a fundamental representation of the Lie algebra on itself. It is called the adjoint let us denote the map as adjoint, the map from G to end G, which is defined as follows: an element X, an element of this Lie algebra. We construct a linear map on the Lie algebra by the formula xy. Okay. So you see, for each x, we construct a map which maps y to xy. At x, it's a map which sends y to xy. So my statement is that it is a linear representation. What to verify? We have to verify this condition. Adjoint of x, y applied to z should be the same as adjoint of x applied to adjoint of y applied to x minus adjoint to y applied to adjoint of x applied to z. But this is equal to such a double commutator, and here we have to write x, y, z minus y, x of z, and this is the same due to the Jacobi identity. So it's some statement which follows from the Jacobi identity. So this map is a linear representation of the Lie algebra on itself. Okay. Definition. There is a big adjoint action of the group on itself. It is a map from G to automorphism of G. It acts as follows: at of G on H, it is G minus 1 H G. No, maybe. We have to verify the following thing: that adjoint of G H applied to F is the same as at G applied to at H applied to F. This is a condition of the action of the group on the set. So in this notation, we can see that G as a set, and we define the action of the group on the set, which is also the group. So we have to verify this condition, and using this formula, what is written? The left-hand side is G H F H minus 1 G minus 1. I inverted GH, and it is H minus 1 G minus 1. Okay. On the right-hand side, we have G H F H minus 1 G minus 1, and it is the same. Okay. Now we have to remind what is the relation between the Lie algebra and the Lie group. Do you remember? Sorry? How are they related?
The tangent plane on unity.
Yes, tangent space at the unity. Unity. Here it is a tangent T E of G. I like to design another copy of our group, but it is the same group. The joint action of the group has the unit element as a stable point. Okay? So in general, this map adjoint with some element G acts as a diffeomorphism on our Lie group, on a manifold, on the Lie group, which is a manifold. And the unit point is the stable point of this action for all elements of G. Is it clear? If not, it's better that I comment all the words, because it's very simple, but maybe not evident. So my statement is that this map at G, for the fixed G, it's a map from a group to itself. Okay? So it's an automorphism of our group. It's a map. It is a diffeomorphism, and it is important, but firstly, it's a smooth map from our group to itself. My statement is that the image of the unit element is the unit element. So the unit element is a stable point of this map or the action. Okay? It means that the tangent space at the unity is mapped to the tangent space to the same tangent space. So the infinitesimal adjoint action of the group on itself define the action of the group on its tangent space. Definition. The differential of adjoint, the big adjoint at the point E, it's the differential map. Okay? There's a map, the finite map, which is the adjoint action, and its differential acts on tangent vectors. So it acts on infinitesimal curves at the point. So there is an action on the tangent space, which is the Lie algebra. Defines the action of G on the Lie algebra. Let us consider this action in the case of G-Len group, the group of linear transformation. G is G-Len. It means that we represent all operation by matrices, by multiplication of matrices, and so we can consider all such objects just inside the linear space of matrices, and the exponentials are clear to calculate. So we represent the element near unit point. So G acts on H. So H is just 1 plus epsilon of A. And we identify A as an element of tangent space to the unit, which is the Lie algebra G. Okay. Then we consider the big adjoint action G on H is G 1 plus epsilon A G minus 1, and it is obviously 1 plus epsilon G A G minus 1. So it illustrates exactly that the action of G on 1 is 1. So the unit point of the group is the stable point. So we get again the element of the same form with small epsilon. And this represents the action, the differential of the joint action on the element of the Lie algebra. You see? So it's again the conjugation, but we now consider A as an element of the Lie algebra. So the adjoint action of G on A is also G minus 1. But we will go further, and we now consider an element G also at the vicinity of the unit element. 1 plus eta B. And B is also an element of T, G. And we'd like to consider the differential with respect to this parameter. So we consider at G minus at E divided over eta, and it would be the commutator. Please verify. Applied to A, and it is. So my statement is that the infinitesimal part of the adjoint group action on the Lie algebra is the adjoint action of the Lie algebra on itself. Okay? And I used it in consideration of the Adler-Kosten-Syme scheme for the full symmetric Toda system last time. So this is needed for our consideration of integrability. So, but here this is very direct and straightforward. Let me remind you the principal points of the application scheme and the full symmetric Toda system. We considered the GLN Lie algebra as a sum of two Lie subalgebras, B plus and SON. So this was G plus and G minus in the general scheme. And we used the lemma. It was the following lemma. Just a moment. I need a map from S of G to S of G plus. In our case, it is B plus, which is defined. You remember that SG is SG plus G minus SG. So the map tau, it is a projection to this summand, and it is also useful for us. Useful for us to interpret this tau as a restriction of our functions. So we have our space G star, and in the space there is a subspace which is the ideal of G minus. The subvariety, all functions from G minus are 0, take 0 values. Okay? So it means that all functions which contains G minus monomials are 0 on this subspace. So this projection to the summand is the same as the restriction of the space of functions to this subvariety. And this statement was the following: if f and g are functions from g s of g, which are invariant with respect to the action of the Lie algebra G plus, and f of g are in involution with respect to the Poisson bracket in this algebra, then tau f, tau g are in involution in this subalgebra. So there's a function in this subalgebra after the projection. So there is so you see this projection is not a Poisson map. It doesn't preserve the Poisson structure. So it is not obvious at all that the images of these projections commute with respect to the Poisson bracket on this smaller Lie algebra. But it's the fact. I have demonstrated it, and we will use it in the case of the full symmetric Toda system. Then it was a construction theorem. We considered delta k of lambda as a determinant of L minus lambda E k, which is given by A was lambda and N minus lambda, N1, A1N. So it's a complete Gillian Lux operator when we subtract the unit matrix, and then we take we take such submatrices. So we cut k first columns and k last lines, and we take this submatrix, upper right corner of our matrix, and calculate it determinant. So it's some polynomial on lambda. It is lambda n minus 2k e k n minus 2k plus 2k minus 1 k n minus 2k minus 1 plus etc. plus lambda 0 k 0. So the first theorem was that all this set of coefficient commute with respect to Gillian Poisson Lie bracket. And the second statement was that the ratios of the coefficients of the same partial characteristic polynomials, Ek I divided by Ek J, are B plus invariant functions. So, and what it means that there is an action of the group B plus on GLN, which is the adjoint action. Okay, so if we consider some element x GLN, then and B from B plus, then we consider just the adjoint action of B on x, which is Bx B minus 1. Okay. Now our space is a dual space. So there is an identification between them. So let us identify it with GLN by the with the help of the scalar product, which is trace xty. Okay. So with the help of the scalar product, we can identify the dual space with itself. So we can define. So it means that the elements of the dual space are just also the matrices, and we have to define the action. So there is a dual action if there is some map at B is an element of endomorphism of G, and there is a dual action of G star. Okay. How it is defined? So add star B on Xi applied to X from G as Xi applied to add Bx. So, and now if we use this identification, then the adjoint action of B on X Y, it should be X from adjoint just B on Y. And now it has the trace of X transposed G, I'm sorry, B, Y, B minus 1. And it is the same as transposition, trace of B minus 1 X transposed B Y. You see? It means that joint action of B on X, if we identify G and G star, is B transposed x b minus 1 transpose. So I have to represent this as the action of at star b of x with y. This, if I understand well, just this expression. Let's return to the statement. So I demonstrated that the ratios of coefficients are invariant with respect to the action of the group, of the Lie group B plus. And even it was the following thing that I considered delta k depending on lambda, which was constructed with b adjoint b of L, like this. And I demonstrated that it is some function depending on b, delta k of lambda just of L. And it means that all coefficients of such a function, all coefficients on lambda, they are multiplied by the same function depending on the element b. No, and it means that the ratios of such functions are invariant with respect to the action of the Lie group. And to calculate this, I used some property. So in fact, so I started by this, and even by a little bit different construction. So
this key is character or something?
Yeah, sure. So do you remember I started by such a statement that L of Eij is the same as the commutator of Eji. What is written here? Here I calculated the matrix, which is the sum of matrix units with the Poisson bracket. I'm sorry. Okay. Eij. But it means that we consider the action of the Lie algebra on matrix elements of the matrix L. So this Eij is an element of the Lie algebra, and it acts on matrix elements of the matrix L. Okay. Here I have written another action of the same Lie algebra, but on matrix units of the Lie algebra of the Lax operator L. Okay, so this Poisson bracket represents the action of the Lie algebra GLN on matrix entries of the Lax operator, and it acts by the Poisson structure. And here is written another action. If you consider the Lax operator as a matrix with elements which are functions on our phase space, we act on this matrix as on a matrix. So we consider its commutator with the matrix unit. Okay, so it's a different way to act by the Lie algebra GLN on this aggregate Lax operator. So this is a statement that two actions of the Lie algebra on the same object coincide. And so it is useful to demonstrate a lemma. So it's better to write it in the following way, that small adjoint action of the element Eij on L, but let me use annotation, is the small adjoint action of Ji, but let us denote it with tilde because it's a different action on L. Now we consider the action. So this is the equality of two actions of the Lie algebra, but there are Lie groups which can be obtained by exponentiation of this Lie algebra action. And it means that if the infinitesimal action coincide, the exponential will coincide also. But now the exponential of T Eij on L will produce the equivalent action, equivalent adjoint action of such group element on the Lax operator. Okay, so now we consider the element from the B plus, and it means that such element is an element from B minus. It's a lower triangular barrel subgroup. And we demonstrated this just by linear algebra arguments. You remember I calculated some commutators and demonstrated that. Demonstrated this formula with this action. But now we know that this and this action coincide, and considering infinitesimal version, I obtain this. So if this is true, then the action of this group preserve the ratios of coefficients, and it means that the infinitesimal adjoint Lie algebra action also preserve the ratios of coefficients. Okay, and now I'd like to finish the statement. The resulting theorem, let Ls be the symmetric 1, 1, 1n, 1, 2, 1n, 2, 2, and n. Remember, it's a Lax operator for the full symmetric Toda system. Its difference with the initial one is that so it's symmetric. We also consider its matrix entries as function on the dual space. Then G K I, which is I K I divided by I K 0, are integrals in involution. So, and the principal part of the proof is to show that remember tau, this projection. Tau of L is Ls. And it means that tau of j k I constructed from L is just j k I constructed from Ls. Do you understand now the difference between functions constructed from the symmetric matrix and functions constructed from the initial full GLN? So they are different. Let me write it. I think that n equal 3 will be sufficient. So we have 1, 1. No. I'm sorry. So when we consider the such a chopping, so it's delta 1 of lambda, it is lambda square E1 plus lambda minus lambda delta 1, 3, 1, 3, 3, 4 plus delta 1, 2, 2, 4 and plus delta 1, 2, 3, 2, 3, 4. You see, there is an element here which enters this part, and tau of delta 1, 2, 3. So it is 1, 2, 3, 3, 4 with A3, 3, 2 just replaced by A2, 3. All other elements are the same, but you see the general consideration of the Gelfand-Zeitlin subalgebra states that this element commute with this one. After this change, it is not absolutely obvious. In principle, the statement is about this. That this substitution doesn't affect the commutativity, but what was central before doesn't remain central.
Can you explain how did you calculate this determinant?
The determinant is the free term in this characteristic polynomial, in this partial characteristic polynomial. Free term, it is always the value at lambda equals 0. Okay? the determinant. So these are the number of rows, and these are the number of columns. First, second, third row, second, third, and fourth column. So that this replacement means exactly this map.
So this replacement you are doing.
Yeah. Yeah. Let me say a little bit more about this decomposition. Here, this decomposition. So B plus, it is the Lie algebra generated by Eij for I less or equal to j. Okay. SON is the Lie algebra generated by Eij minus Eji for, I don't know, less or equal to j. Okay. So now we should we'll define this element as Fij. So we now should represent all monomials and all polynomials on Eij as polynomials on Eij with I less or equal to j, or only differences. Okay? So if the projection of Eij is equal Eij for I less or equal to j, and the projection of Fij is equal to 0. So the projection of Eij minus Eji is equal to 0. And it means that the projection of Ij is equal to Ji is equal to Eij if j is greater to I. So how this projection works. So it acts on generators by these formulas. And now we have to apply this projection to the Lax operator, to the entries of the Lax operator. Because it's a matrix, those entries, matrix entries, are functions on our space. So we apply tau to functions. Okay? E11, 12, 13, 14, 21, 22. So it is applied to all the upper corner as an identity. So because this upper corner is the element of the upper barrel subalgebra, so tau on such elements acts as an identity. E11, E12, E22, E44, E14. But then they apply them to the lower corner. We have to use this condition. Because these generators have to go to 0. The generators of the Lie algebra SO, of the orthogonal Lie subalgebra, have to go to 0.
J greater than I?
Yes. So we know that T, E, Ij minus Eji, it's a linear map. Eij minus t ej I. Okay? But we know that this goes to eij. So if j is greater than I, this is an element of the barrel subalgebra, upper barrel subalgebra. So tau acts on this element identically. It will ij minus t eji. And this is 0. So it's an effect that we consider the projection along the orthogonal subalgebra. If it will be another, for example, we can consider such a decomposition. If we consider such a decomposition, then this will be 0. But in our case, so it's this element. So it means that the projection, the tau applied to this element is E12, E13. So it's a symmetric matrix which we need for describing the full symmetric Toda system. Okay? So it's principally the end of this construction. And now I'd like to comment how we obtain the open Toda system as a reduction or restriction on the full symmetric Toda system. Okay. So our algebra is the symmetric algebra of B+. So we work in this Poisson algebra. And I'd like to consider another F0, which is also a polynomial algebra, but generated by EII and EII plus 1. So it means that I consider only elements on the principal diagonal and on the first subdiagonal. And with the Poisson bracket is the following: EII, EJJ is equal 0, EII with EII plus 1, EJG plus 1 is also equal 0, and EII with J plus 1 is equal delta ij ej plus 1 and minus delta if j is equal I minus 1 I minus 1 j the same j plus 1. Okay. Something like this. It means that I consider only, so it's a Poisson bracket and Flaschka coordinates, if you remember, for the open Toda chain.
Coordinate have some A and B.
Yes. A on the diagonal and B on the subdiagonal. So these are A and these are B. But we now have to realize it at some reduction procedure from this one.
This like EII plus 1, EJJ. The same thing with the delta.
Here.
Yes, I'm saying like instead of this, if you have like EII plus 1.
The same. It's a skew symmetric. You remember, Poisson bracket should be skew symmetric. So there is such a procedure. Definition. The subspace an ideal means that with respect to the ring structure, of a Poisson algebra F is called a Poisson ideal if for all elements from I and all elements from F the Poisson bracket of A and G is an element of I. Okay? If you remember what is an ideal in the ring, so it's quite direct generalization to the Poisson framework. So it means that you see that we consider an ideal, so it means that we can multiply the functions from I by all functions from F. But now we ask that the Poisson bracket of element of an ideal with all functions should lie in the ideal. You see? So in this case, lemma if I is a Poisson ideal, then I is a Poisson algebra. Just a quotient. So we have some ring, we have some ideal, we can consider the quotient, and the quotient in geometrical terms is always the restriction. We can consider the restriction of our functions to the spectrum of this ideal. Okay? But why it's true? Do you understand? It's quite evident.
And why this is a Poisson algebra?
Yes, yes. So the idea is very simple. We have to restrict Poisson bracket to the quotient. Okay? The same Poisson bracket. The problem is to demonstrate that it's well defined. That if we add to some function some element of the ideal, what is the quotient? It is the space of equivalence classes. And we have to add I. So the set of all such elements is the class of F. You see? F from I. So we couldn't distinguish between different elements of such type. And so we have to demonstrate that the Poisson bracket of F plus I and G plus J.
What do you write here after I minus?
No. It's, just all set of such elements is a class of F in the quotient. Understand? What's the quotient ring?
This F small is
F is a representative of the class.
In fact, we should say the reason we define ideal is that we hope this quotient be a nice definition.
Yes, of course. So, and the calculation is very simple. plus fj plus ig plus ii, and all this part, it is an element of I, because it's a Poisson ideal. Poisson bracket with elements j and I are also elements of this subspace. So it means that the Poisson bracket between different representatives lies in the same class. It means that it is well defined on the quotient space. In our case, let us consider the ideal generated by ij with I less than j minus 1. Okay? It means that in our matrix 1, 1, 1, 2, 1, 3, 1, 4, etc., we consider all these elements. So we consider an ideal in the commutative sense generated by such elements. My statement is that it is a Poisson ideal. Okay? Poisson ideal. How to verify? Home task.
Home task to check that this is a Poisson ideal.
Yes, it's a Poisson ideal. So if you consider Poisson bracket of such elements, you get elements of the same type. But for our aims, it can be used. So my statement is now that S of B plus, if you consider the quotient with this Poisson ideal, we get exactly F0. So we can restrict our functions to the subvariety where all these functions are zeros. It is the same as to consider three diagonal symmetric matrices. And obviously, all Hamiltonian vector fields preserve this subvariety because it's a quotient with respect to the Poisson ideal. So, and this is explanation how the open Toda chain is included into all this story of the full symmetric Toda system. So it's some Poisson subvariety, and it is defined by this quotient with respect to the Poisson ideal. Okay, a few words about the algebra. I suppose you started to understand that the integrability is closely related with such algebraic question as the problem of invariance, finding invariance in some actions of group Lie algebras, etc. And I'd like to remind you such a question, remark. So when we consider it, the Poisson algebra S of JLN, we consider it its Lax operator, which is the sum ij eij, and we stated that the center of S of JLN is generated by traces of L. So it's some polynomial ring, and we can easily find its generators, which are just the traces of such a Lax operator. And what it means algebraically, I don't know. For me, it's very important.
Over this notation, G means center.
This is center, JLN. So just the symmetric algebra of JLN, which is the algebraic function on the dual space. So there is a Poisson structure on this commutative algebra, and we are interested in the center of this Poisson algebra. First of all, it's the same as the space of invariant functions, JLN, or the same JLN with the action of the Lie group JLN, with all the details we discussed at the beginning. So it's some basic question in algebra. What are the invariants of some action? How it is organized the quotient space? So in many different subjects and problems it appears. There is another question. So let us consider the nilpotent Lie algebra, and it's symmetric algebra, and the question will be, what are the invariants or the central elements in this algebra S of n plus. N plus, as you remember, is the Lie algebra of upper nilpotent matrices Eij with I less than j. It differs from the Borel subalgebra, so it doesn't contain the diagonal, the Cartan elements. And the question is absolutely non-trivial. If you so if you just try to calculate such functions, they are not elements of this subalgebra. You understand? So if you just try to calculate this, even the trace is not an element of this nilpotent Lie subalgebra. So this construction doesn't serve to solve this question. And it appears that our chopping procedure, that delta k of L, just the determinant of L of k. Yes, for k, this is L. I'd like to, okay, this is k. For k greater than n over 2, generate, so it's this theorem, generate z of s n plus. How to demonstrate it? Proof. Do you remember the statement that delta k of lambda of L so we demonstrate that at B of L is he B of delta k lambda of L. If B is an element of the nilpotent, then here of B is equal to 1. So, and if you remember, I considered B as an element A, B, C. Then I acted by B transposed on the matrix L, B transposed minus 1. So in B transposed and my character of B was the ratio of determinant, if I remember, something like the determinant of A divided by the determinant of C. So if we consider the nilpotent element, here we have the not unit matrices, but the matrix A transposed is 1, 1, 1, something here, something here. So its determinant is 1. For the exponential of the nilpotent matrix, its group, this group element has a determinant 1. So this character for the action of the nilpotent group is 1, just 1. So these functions are invariant with respect to the action of the nilpotent group. The only thing to do is to extract some coefficients which lies in the nilpotent Lie algebra, in the symmetric algebra of the nilpotent Lie algebra. And my statement is completely simple, that if you get the minors only of the half, not greater than half the dimension, we get here some polynomial expressions in the nilpotent part of our Lie algebra. So my statement is that in this interval of values of indices, these polynomial functions depend only on the nilpotent part of the Lax operator. And they are invariant with respect to the action of the nilpotent group. So it means that they are central. Okay? Your home task 2 will be to construct the center of the B. So there is some subtlety that there is no central element, there are no polynomial central elements, but there are rational ones. So we have to consider the field of fractions. It means that we consider the ratio of polynomials. And the task is to define this center.